All right, hello everybody. So far with trigonometry, we've talked about how we can use these trig ratios to figure out sides and angles of right triangles. And that's pretty handy. But today what we're going to talk about is how we can actually apply this to solve real life problems. Okay, now this is lesson 5 in your notes. This is a bit of a lengthy lesson, so I'm actually going to break this up into 2 different videos. Okay, so we'll do part A today. Now, before we actually start talking about any particular problems, I wanted to define 2 terms for you. The first one is the angle of elevation, and the second one is the angle of depression. Okay, now the angle of elevation, when you hear the word elevation, it's kind of connected to the word elevate. Okay, elevate is like moving upwards, right? If you're feeling elevated, you're moving up. Okay, the angle of elevation is basically the angle between the horizontal and the observer's line of sight looking upwards. Okay, so if someone's looking up at something, then it's the angle between the horizontal. So imagine a horizontal line from their eyes and their line of sight and where they're looking. And I'm going to draw a picture of this in a moment. So don't worry if you can't picture it rather in your head. Okay. Angle of depression. Well, if you're depressed, imagine that you're kind of feeling down. Okay. So the word depression is connected to being down. Okay. That's the angle between the horizontal and the observer's line of sight. Whoops. Looking upwards. No, downwards. Okay, so what I'm going to do is I'm going to draw a picture right now of 2 people looking at each other. And one of these people is going to be standing on the ground. So here's the ground. There's my excellent drawing of a person. And here's another person who's standing on the top floor of a building. So here's like the top floor of a building, and here's this person standing there. Okay, and they're looking at each other. So here's this person looking up at this person, and then this person you can imagine is looking down at this person. Okay, now the angle of elevation is from the person looking up. So that's the person at the bottom, and it's from the horizontal. Now the horizontal actually isn't part of this picture, so we have to draw in, I'm going to draw it in as like a dotted line, an imaginary horizontal from where their eyes would go. And it's the angle between the horizontal and the person's line of sight. That's right here. Okay, this is the angle of elevation. Okay, now sometimes it's not actually an observer. Sometimes it's an object, right? Sometimes it might be like a building, or sometimes the example is like a fire somewhere, and then there's an airplane that's going to dump water on it. So the angle of elevation is from the fire up to the airplane. So you can imagine, pretend that the fire rather has eyes, okay? And that the fire is looking up at the airplane. It's the same sort of idea. Okay? And notice also this very conveniently creates a little right triangle. So that's kind of nice. Okay? Now, the angle of depression is also between the horizontal. So a lot of people think that the angle of depression is this angle here because it's part of the triangle, but it's actually not, because that's an angle between the observer's line of sight and the vertical line. Okay, so we also have to draw in this horizontal here. Always between, both of these are always between the horizontal. Okay, this over here is the angle of depression. Okay, now one thing that you can notice is that these two horizontal lines are parallel to one another. And so these angles, this person from the top, their angle of depression, and this person at the bottom, their angle of elevation, these are actually alternate interior angles, and they are equal to one another. So when one person from the top is looking at one person at the bottom and vice versa, the angle of depression for one person is going to be the same as the angle of elevation for the other person, okay? They will be equal to one another. Now, the reason why I want to go through this vocabulary here is that when we are describing a situation that can be solved using trigonometric ratios, oftentimes these two words are used to describe part of what's going on in the problem. And so we need to be able to sort of picture what's happening so that we can perhaps draw a diagram of what's going on. Okay, so what I'm going to do, there's sort of 5 problems in this section. I'm going to skip around a little bit. I'm going to do questions 2 and 3 in today's video, and then I'm going to do questions 1, 4, and 5 in the next video. Okay, so I'm going to move on to the next page right now. All right, so here we go. The angle of elevation, there is that term again. So I'm just going to underline that. The angle of elevation of Sandra's kite string is 70 degrees. If she lets out 55 feet of string and is holding the string 6 feet above the ground, how high is the kite? Okay, well, when you're approaching these problems, the first thing you want to do is you want to be able to draw a diagram of what's going on. Okay, so if you can imagine what's going on here, try and ignore the numbers for now. What's going on is you've got this girl, Sandra, and she's flying a kite. Okay, so what's important here? Well, Sandra's standing on the ground, so I'm going to draw the ground. Here's the ground. Here's Sandra. She's holding this kite string. So here's the string, and here's the kite. Oh, I'm so bad at drawing. There we go. Okay, and basically that's the picture of what's going on. Okay, now what we can do is we can start to pick apart the details of the problem and add those into our diagram. Okay, so her angle of elevation is 70 degrees. Well, the angle of elevation is from her line of sight, or from where the string starts up to the kite and between the horizontal. So that's, we don't have the horizontal in. We got to draw that in. That's right here. Okay, this is 70 degrees. Okay? If she lets out 55 feet of string, well, that means the string from her hands to the kite is 55 feet. So this over here is 55 feet. Okay? And is holding the string 6 feet above the ground. Well, that means that the distance from here to here is 6 feet. How high is the string? Well, what we're being asked for is essentially, what is this height? How tall is that? Okay, well, this is now a right triangle. Okay, and we know what this is. This is 6 feet. So if we can find this, I'm going to call this x, then the total height would be whatever this is, x plus 6. And that's what the question is asking. Okay, now x is part of a right triangle. And in that right triangle, we know an angle and we know another side. That means that we can now use trigonometry to be able to find the value of x. And that's what we're going to do now. Okay. Now, when we're trying to find the value of x, well, this is just like finding a side length in any right triangle. So where do we start? Well, we start by labeling. We got to label our sides. Okay. Now I'm going to use this angle of 70 degrees to do my labeling, because if I'm trying to find a side length, I've got to use an angle that I know. So firstly, here's my right angle right here. I'm going to go across from it. This is my hypotenuse. Okay. To find my opposite side, I start with the angle I'm using and I go across from that. That's my opposite side. And then the one that's missing is my adjacent. And that's, again, the one that's beside the angle. That's not the hypotenuse. Okay, so I've labeled my triangle. Now I've got to pick a trig ratio. So my trig ratios, I'll write them up here. That mnemonic, so, ka, toa. Okay, now the side that I'm looking for is my opposite side. So the trig ratios that use opposite are so, sine, or toa, tan. Okay, I can't use cosine in this example because it doesn't involve the opposite side. And to figure out which of sine and tangent rather that I can use, I've got to think about, well, what's the side that I know? The side that I know is the hypotenuse. So if I know the hypotenuse and I want the opposite, I've got to use the trig ratio that involves opposite and hypotenuse, and that's sine. So I'm going to write that down. Sine theta equals opposite over hypotenuse. And now I'll fill in what I know. Okay, so what do I know? I know my angle, that's 70 degrees. And I don't know what my opposite is. I'm going to label that x. I do know what my hypotenuse is. That's 55. Okay, well now, sine 70, that's just a value that's stored in the memory of my calculator. So now I'm going to pull out my calculator. Here it is. And it's in degree mode. I'm checking that. I'm going to go sine of 70 equals, and I get 0.94, let's say, 0.94. Okay, I'm going to remember that. Rounded to the nearest hundredth. So 0.94 equals x over 55. And if you wanted to convert the 0.94 into a fraction, remember you can always make the denominator 1. Okay, well now to solve for x, you have to look at what's being done to it. I'm dividing x by 55. How do I undo that? I multiply both sides by 55. Okay, cancel. And I get that x equals 55 times 0.94 divided by 1. And that is Well, let's see. I got to pull out my calculator again. 55 times 0.94 divided by 1, 51.7. Okay, so x is 51.7 feet. Okay, well, remember, that's just this part. The total height is also going to include the 6 feet off the ground from where the string is being held. So the total height, is equal to 51.7 plus 6, which works out to be 57.7 feet. Okay? So this is this problem. A big part of it, though, is being able to read the question and translate it into a picture. Okay? So we're going to practice that skill. We're going to practice the skill of just translating words into a picture. All right, let's try one more. All right. The horizontal distance between two clothesline poles is 3.4 meters. When wet clothes are hung in the middle of the line, it sags at an angle of depression of 6 degrees. How long is the clothesline? Okay, so we've got a clothesline. So that's like what you would put laundry on to dry on. And it's being held up by 2 poles. So I'm going to draw the 2 poles. And here we go. Here's one pole. And here's another pole. Okay, and here's the line. Okay, so it's like a string. Okay, and here's the ground, by the way. Right, so maybe these are like a little bit thicker, actually. Probably a little thicker. Maybe I'll color them in a little bit. There we go. My excellent coloring skills. There we go. Okay, so there's the 2 poles. Okay, now this dotted line is a string. So when you hang some clothes in the middle of it, let's say we hang a t-shirt in the middle. So I'm going to draw a t-shirt. This is my terrible drawing of a t-shirt. Here we go. Let's see. And it's right in the middle. Oh boy. Oh, it's a very short, it's like a crop top. Okay. And here's like a little clothespin. Okay, so this is right in the middle. We're going to pretend it's right in the middle. Then what happens is that the line sags a little bit. And I know that my drawing isn't very good, but we're going to say that this is right in the middle of the line. Okay, so this is a picture of what's going on. Now that we can kind of picture what's going on, now we've got to start to fill in some details. Okay? All right, so firstly, the horizontal distance between the 2 lines between the 2 poles rather, is 3.4 meters. So that's this piece here. That's 3.4 meters, okay? When wet clothes are hung in the middle of the line, it sags at an angle of depression. So I've already drawn this horizontal line in there, but this angle of depression, remember, is between the horizontal and sort of the line of sight, if you can imagine that these things have eyes, between the pole and the t-shirt. Okay, this is 6 degrees. Okay, now you may not see a right triangle yet, but if we draw this little guy, and remember, I didn't make the drawing very good, but we're going to picture that this is right in the middle. That makes a right triangle. Okay, and if it is in the middle, if it's exactly in the middle of the 2 poles, then this part should be exactly half of the distance between the two poles, which is 3.4 meters divided by 2, which is 1.7 meters. Okay, well now what we have, and I'm going to redraw this over here because the drawing is a little bit tiny. What's really important here is this picture here. Right, here's a right triangle. This is 6 degrees, and this is 1.7 meters. Okay, now what we're being asked for is the length of the clothesline. Okay, that would be the length of this entire thing. So maybe I'll actually switch colors so that I can just draw it in here. So we're being asked for the length of this, what I'm doing in red. Okay. Now, how can we find that? Well, if we can find this part of the triangle, the length of the clothesline is going to be double that, because what you'll see is that we have this exact same triangle sort of in the mirror image on the other side. Okay, so our goal here is to find this red line. And if we can find the length of that red line, then we can figure out the length of that clothesline. So that's what we're going to do. I'm going to switch back to black. All right. Well, how do we do that? Trigonometry again. Okay. Here we're looking for a side length. So I'm going to call this side length X. And we start by labeling our sides of our triangle. Okay. Again, if I'm looking for a side length, then I must know an angle and a side. So I'm going to use the angle that I know to label my sides. And I'm going to start with my right angle, which is right here. I'm going to go across from it. This one is my hypotenuse. Okay. To figure out the opposite side, I start from my angle that I know. I go across from that. That's my opposite side. And then finally, the third side, which is the 1.7 meters, this is my adjacent. And if I write out my so, ka, toa, okay, in this case, X is my hypotenuse. So I need to use a trig ratio that includes hypotenuse. And the ones that include hypotenuse are sine and cosine. So I can't use tangent in this case. And to figure out which of the two, sine and cosine, I can use, I've got to look at, well, what's the other side that I know? And that happens to be the adjacent side. So in this case, I've got to use the trig ratio that includes adjacent and hypotenuse, and that is cosine. So I'm going to write out cosine. Cosine theta equals adjacent over hypotenuse, and I'm going to fill in what I know. So I know that my angle is 6 degrees, and my adjacent is 1.7, and my hypotenuse is X. I don't know what that is. Okay, so I'm going to go over to my calculator now and figure out what is the cosine of 6 degrees. And that is 0.9945. All right, 0.9945. $0.9945 equals 1.7 over X. And remember, this 0.9945 is over 1. So this is a scenario where our unknown is in the denominator. So you've got to now go in one of two directions, okay? You can either flip both fractions. So you can go this way, where you, instead of writing 0.9945 over 1, you write 1 over 0.9945. But then you'd have to make that equal to, instead of 1.7 over X, it would be X over 1.7. So you could solve that, okay? To solve that, well, what are we doing to x? Now we're just dividing it by 1.7 because now it's in the numerator. So I'm going to multiply both sides by 1.7. Okay, and these cancel. And then what we end up with is x equals 1 divided by 0.9945 times 1.7. And that is, let's see. Now, one thing you can do actually is if you still have that, oh no, I'm going to do 1 divided by that. I was going to say you can use this answer that's still in your calculator, but let's just leave that for now. So 1 divided by 0.9945 times 1.7. And that works out to, I'm going to round this to the nearest hundredth. Okay, so the nearest hundredth position is 2 decimal places. That's where the 0 is. So if I'm rounding to the nearest hundredth, what I need to do is look one place to the right of it and to see if that's going to round up or down. Now, this is a 9. So if the digit to the right is a 5, 6, 7, 8, or 9, then this 0 will round up, which in this case it does. So to the nearest hundredth, this is 1.71. Okay, so x equals 1.71 meters. Okay, so that's the value of x. Now remember, x isn't the length of the clothesline because this is just 1.71 over here. This is also 1.71 though. So the total length of the clothesline is 1.71 plus 1.71, which is 3.42 meters. Okay? Now the other way that you could solve this, by the way, if you don't want to go flipping both fractions, is from this point, you could take, if we're over here, you could take some steps to get x out of the denominator, right? So if you're dividing by x, you could now multiply both sides by x. Okay, so to undo division by x, I'm going to now multiply both sides by x. So I'll just go times x, and these guys will cancel. And what I end up with on the left is 0.9945x divided by 1 is just the same, so I'll leave that out, equals 1.7. And then now what I'm doing is I'm multiplying x by 0.9945. So to undo that, I need to divide by 0.9945. And I need to do that on both sides. Okay, and then these will cancel. So we'll just be left with x. And if I put this into my calculator, the 1.7 divided by 0.9945, I'm going to get the same thing, 1.71. So I'll just do that quickly. And there you have it. You get the exact same result. Okay, so either way you want to solve that is fine. Up to you. We got 1.71. Okay, and then you still have to figure out this total length over here. All right, so I'm going to sign off on this video for today, and we'll go through some more problems next.